Hi everyone, we are starting a new unit in this video, Biomolecules Part 1, Carbohydrates. There are actually four biomolecules that I want to talk about in organic chemistry too. Carbohydrates, and then we will see lipids, proteins, and nucleic acids. So biomolecules are typically very large molecules that are important for life. And we're dealing with carbohydrates right now because we had just in the previous two units talked about alcohols and aldehydes and ketones. And carbohydrates have all those functionalities. For this video, we are going to concentrate on a couple definitions: carbohydrate, monosaccharide, and sugar. We're going to see how sugar chemists and biologists draw them as Fischer projections, and they don't typically work with R and S designations when they talk about stereochemistry. They talk about D and L, and I'll show you how to assign those. So the first thing is carbohydrates, the definition. Polyhydroxyl, or I think it's better to say polyhydroxy, aldehydes and ketones. Okay. So the definition of carbohydrate is structural based, but there's a caveat. Polyhydroxy aldehydes and ketones, or I should say and, molecules that give these upon hydrolysis. And I'll show you what I mean by this through structures. And molecules that give these, the polyhydroxy aldehydes and ketones, upon hydrolysis. Okay. Before we take a look at a carbohydrate, in particular glucose, let me show you very simple carbohydrates. The first one is glyceraldehyde. So there's your aldehyde. So I'm drawing this as vertical lines and horizontal lines. Okay, let me just double check. Yep. This is called glyceraldehyde, common name. Does it satisfy the definition for a carbohydrate? Yeah. More than one hydroxyl group is an aldehyde. Don't forget that CHO is C double bonded to O and with a hydrogen. I drew it like this because this is a type of drawing called a Fischer projection. And what it really means is that the molecule has wedges and dashes. All the vertical lines are going to be dash, all the horizontal lines are going to be wedge. And now we can assign stereochemistry. We can assign R and S. Now, I don't have my models with me, but how do we get this with a model? You could take your tetrahedral carbon. I wonder where my models are. Ah, here we go. Normally when you draw a tetrahedral carbon, you have one wedge, one dash, and two lines. But you could still show this kind of drawing with two wedges and two dashes by holding your molecule like this. Okay, so I don't have the groups, but I do have the tetrahedral carbon. And if I hold it like this, do you see how we have two hydrogens pointing towards us and the two hydrogens going away from us? Okay, but it's still, as you know, the tetrahedral molecule. Okay, just hold it like that. And we might as well practice a little bit R and S. Priority number 1, oxygen. Priority number 2 is this carbon that's connected to oxygen with a double bond. Priority number 3 is this CH2OH. but H is towards us. So I like to say it looks S, but it's actually R. The chemists know this as an R stereochemistry. Biologists know this as D. Okay. So what does D stand for? D stands for, I just want to make sure I get this right. D stands for dextrorotatory. L is the opposite. L is levorotatory. From the Latin for right, dex or dextra, Latin for left, levo. This is D, and the way that scientists assign carbohydrates D or L is they look at the hydroxyl group on the second to last carbon. If OH on, we call that the penultimate carbon, is to the right, then the designation is going to be D. Okay. You wouldn't want to think that all D carbohydrates are also R carbohydrates. We're going to see carbohydrates that have multiple chiral carbons, and we're going to still focus on the penultimate carbon, the second to last carbon, and see where that OH is. And if it's on the right, it's going to be called D. Okay? So that's glyceraldehyde. Then we can assign D or L for glyceraldehyde. This is D, right? Because the OH is on the right. The other way that you can remember Fischer projections is that, see, every horizontal line is a wedge, so it's almost like the molecule is giving you a hug. Okay. Now, there is a carbohydrate that does not have a chiral carbon, and that is this one here, but it's still a carbohydrate. Okay. And yep, that is a carbon in the middle, right? So this has 3 carbons. This is called dihydroxyacetone. So these are our 2 simplest carbohydrates. This dihydroxyacetone has no chiral carbon, though. There is no D or L designation for this molecule. Okay, what else do I want to talk about? All right. There's another way to sort of categorize carbohydrates, and I think it's best just to show an example. This is called an Aldo Triose. So Aldo, hopefully from you know that it's aldehyde. And Triose, tri, because there are 3 carbons. And this one is a keto triose, because you have a ketone group. Okay, good. Let us talk about the most popular carbohydrate, and that is glucose. And we're going to draw D-glucose. And it's going to be D because of the second to last carbon, the OH is going to be to the right. Glucose is a 6-carbon molecule, and we have an aldehyde group at the top. Okay. I normally don't do this, but I'm going to draw the letter C. Okay, there's a reason for that, and you'll see in just a bit. And then we have a pretty long line because we need 4 horizontal lines on glucose. 1, 2, 3, 4. And we're still going to go by the Fischer format. So every horizontal line is wedge, every vertical line is dash. Now in real life, if you conform the molecule to do that, then the molecule will curve upon itself like a crescent shape. Obviously, that's not how it looks like. That's not a very stable conformation, but it is the conformation that we're going to use when we think of this as a Fischer projection. So they're drawing it out of convenience as a Fischer projection. Right, right, left, right. Okay. The OH is on D-glucose, on the carbons that are chiral, right, right, left, right. These other bonds, you gotta put hydrogen, or else your professor's gonna think that those are methyl groups. That is D-glucose. The formula is C6H12O6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, 11, 12. All right. Okay. Why did I say that carbohydrates is a good biomolecule to start with after we've talked about alcohols and aldehydes and ketones? Because look at D-glucose. You have a carbonyl group and you have a bunch of hydroxyl groups. The reaction that you want to know for carbohydrates are the hemiacetal and acetal formation. So we're going to review, not in this video actually, I don't want to jump too far ahead, review hemiacetal and acetal formation. I cover those in Unit 2, the unit preceding this one. Okay. Let me just make sure I'm not missing anything. Okay. I'm not going to show you how or why this happens because I do still have a couple more definitions to discuss and a couple introductory things to discuss. But when you have this in water, and it will go faster with acidic water, so let's use HCl. Okay, you're going to get a cyclization because I'm going to consider this as acyclic glucose. Okay. By the way, do you know why it's D now? Second to last carbon, we have the hydroxyl group to the right. Okay. I'm going to number actually the carbons. Okay. And again, I'm going to draw the ring version of D-glucose, but we're going to, on a different video, on the next video, discuss how this happens. Right now, I just want you to have a picture of what glucose looks like in real life. Because in real life, when you digest glucose, it will cyclize. And it will cyclize into a molecule that looks like this. This is just one stereoisomer. I'm not drawing the other one, but don't worry about that. And also don't worry, whoops, man, messed that up. Also don't worry about why I'm drawing it like this, where we have two lines, one up and one down. Okay, I'm not specifying equatorial or axial, if you remember your chair conformations. We're not dealing with that right now. What I am concerned about at this point is, do you know where every atom is when you go from the acyclic to the cyclic glucose? Okay. Well, let's number the atoms. Where's 1? 1 is actually this carbon right here. And I'll show you why I think that in just a bit. Let's go around the ring. 2, 3, 4, 5, 6 is not within the ring. So what's important to me is, where is this carbon number 1, or why do I think this is carbon number 1? And where do these oxygens come from? Okay. This came from a cyclization in which this oxygen attacked this carbon. All right, so don't worry yet. Okay, don't worry yet about the mechanism. Okay. Again, we will do that in the second video. Worry about where every oxygen and carbon is when you go from acyclic to cyclic. You see how this carbon 5 has the OH? So that OH, this one that I'll circle, or specifically not the OH, but the O. That O is this O right here. And it attacked carbon number 1. Carbon number 1's here. So what is this oxygen? That oxygen, I'll put a star. That's the carbonyl oxygen that it became the hydroxyl group. What do we know about this functionality right here? Does that look familiar? That's a carbon with an OH and an OR. Carbon that's attached to the hydroxyl group and an alkoxy group and 2 other bonds. Now, it is true that this alkoxy group continues on and closes a circle, closes the cyclic system, but it's still considered an OR, alkoxy. This is the definition or the general structure for a hemiacetal. You can draw the mechanism. If you know the mechanism to make a hemiacetal from Unit 2, you could apply that to here. Now, it's unusual because you have many, many hydroxyl groups. What caused it to make this ring here? How come I didn't use this hydroxyl group to make a 1, 2, 3, 4, 5 atom ring? Okay. Well, 6-membered rings are more stable. And later on, we're going to see that actually we could draw glucose with all of the groups off of the ring being equatorial. Again, don't worry about that. Worry about this numbering system. Okay. Let me see. All right, a couple more definitions. I think we're moving pretty fast. We may have time actually to go over that hemiacetal reaction. Or not. We'll see. You have the definition for carbohydrate. Polyhydroxyaldehydes and ketones, and molecules that give these upon hydrolysis. Do you notice that this molecule right here has no carbonyl group? This is not an aldehyde or ketone. But when you do hydrolysis, you get the aldehyde or ketone. That's what they mean when they write the definition like this, that it could also be the molecules that come from these polyhydroxyaldehydes and ketones. Okay, they just stated it a weird way, or I stated it a different way. It's molecules that you get these polyhydroxyaldehydes and ketones from hydrolysis. Okay, so we could do hydrolysis, and we could show that actually. Backwards, hydrolysis. All right. What are the other definitions, though, that I want to go over? Monosaccharide. A monosaccharide is a carbohydrate that only has one carbonyl group. And then I messed up the spelling. There are 2 C's in saccharide. Okay, it's a carbohydrate that just give me 1 second here. How about that when fully hydrolyzed? Results in just 1 carbonyl group. This is a carbohydrate, but it's also a monosaccharide because upon hydrolysis, it gives 1 carbonyl group. Honestly, the easiest thing to think about when you think about monosaccharides is it's only 1 ring. Okay, let me show you. We have a disaccharide actually in the cover slide. See, that's disaccharide because it's 2 rings, and upon hydrolysis, full hydrolysis, you'll break the rings apart, you'll open up the rings to expose their carbonyl groups, and you'll have 2 carbonyl groups. one for this molecule on the left, which is glucose, and one for this molecule on the right, which happens to be fructose. Okay? We'll get to disaccharides much later, though. Okay, so that is a monosaccharide. And actually, all the molecules we've seen so far are monosaccharides. The D-glyceraldehyde, the dihydroxyacetone, all of that. Okay. Let's go back to glucose, because I think it's important that you be able to assign RNS to every chiral carbon. So we're practicing drawing glucose again. Right, right, left, right, 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 left, right. Put in your hydrogens. Okay. It's definitely D because we're only looking at the second to last carbon. But actually, all four of these carbons in the middle are chiral carbons. Let's assign at least a couple of them. Let's assign, this one's probably the easiest. Okay. And what am I doing? I'm redrawing it. Because it's going to get really crowded when I make the assignments for all these chiral carbons. Or if I do make the assignments for all these chiral carbons. Priority number 1 off of this carbon is here. The hydroxyl group is connected to an O. O beats C beats C. Now we have 2 carbons, but this carbon on top is connected to an oxygen by a double bond. 2. And then this carbon is connected to an O, but singly bonded. This is the third priority, and obviously the last priority is hydrogen. So this first carbon, and we will call it carbon 2. Okay. That carbon has, let's see, 1, 2, 3, it looks S, but it's actually R. Because the lowest priority is pointing in the wrong direction. Okay. You see why I want to do these separately? I'm going to leave this carbon number 3 for you guys at home. 4 is a little bit trickier because you have to walk further along the path to see a difference between the path going to the north and the path going south. So we'll do 4 together. Fischer says all horizontal lines are wedges. Let's put our hydrogen there. We have carbon number 1 here. 2 and 3 may be a little bit difficult. That's where we start. And then we will walk 1 bond away, carbon versus carbon, but it's a tie because they all have OH and H on it. Keep walking, you have a carbon OH. Oh, this carbon right here has 2 hydrogens and an oxygen. This carbon over here is connected to an oxygen and a carbon. So the path going to the south is a high priority. Huh. 1, 2, 3. Again, it looks S, but it's actually R. You have another R. That worries me a little bit. Let me look at this one. You could test yourself, see if you could beat me. This is S. 1, 2, 3. Oh, no. Yeah, it's R. It looks R, but it's actually S. Carbon number 3 is S. Okay. All right. Popular question that I like to ask is, okay, that's Fischer, but what if we draw just a plain wedge dash drawing with 6 carbons? Here's your aldehyde. That's carbon number 1. But we have these other carbons that are chiral that have OHs, and then 1, 2, 3, 4, 5, 6. Off of the 6th carbon, we have an OH. The last carbon is not chiral, so it doesn't matter how you draw the OH, up or down, left or right. Just don't put any wedges and dashes. What we do have to worry about is what is carbon number 2, 3, 4. Oh, did I put too many? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. Oh, here's 5. My bad. And 6. how would you draw the hydroxyl groups on 2, 3, 4, and 5 so it matches your RNS designation? Okay. Draw OH groups with correct wedge dash. That might be a problem that I would put for my after video problems. Another thing is enantiomers. The enantiomer for glyceraldehyde. Okay, we're still using Fischer projection. Drawing the enantiomer for Fischer projection is pretty easy. Just draw the mirror image. So here's your mirror. And CHO, CH2OH. The OH is now closer to the mirror. We have this. I can guarantee you, well, we could tell for sure that this is D, and it is D-glyceraldehyde. This is called L. And if you draw the enantiomer of a monosaccharide, you go from D to L, and you keep the name, L-glyceraldehyde. Okay? So a popular question is, draw the enantiomer of D-glucose. Okay, and name it. Well, whenever you take the enantiomer, you just switch the D to the L, and you keep the name. So yeah, every chiral carbon is going to change. It's still considered a D-glucose, still considered a glucose, but in this case, your enantiomer would be L-glucose. Okay. Honestly, that's about all I want to say for carbohydrates, or at least for the introduction. In the next video, we are going to talk more about the cyclization to make the hemiacetal, and also, I didn't tell you in this video why I drew the OHs the way I did. Okay, because these stereocenters are set either R or S, so these have to match the RNS designations the way that I draw them in this type of drawing. Oh nuts. Sugar. Sugar is a very, very general term, and it just means carbohydrate. Or, if you want, it's based off of really the properties, so it's a sweet carbohydrate. It could be monosaccharide. So let me give you an example. Monosaccharide, fructose. Fructose is a monosaccharide that is sweet, fruit sugar. Or it could be disaccharide as well. Misspelled that, only one S. A disaccharide such as sucrose. Sucrose actually is made up of two monosaccharides, glucose and fructose. Okay. It's very rare. Just like in conversations, we'll say sugar chemistry, what sugar is involved with, cell marker, biomarkers, or blood typing. Those are all carbohydrates, all involving carbohydrates. But really, to be really scientific about these molecules, you should be calling them monosaccharides, disaccharides, or just overall carbohydrates. And then before I leave this video, that is an example of a disaccharide, sugar. It's called sucrose, and you have glucose and fructose. All right, and probably in maybe the third video, we are going to discuss how to make these disaccharides and how to make these linkages. But for this one, it's just an introduction, and I'll see you on the next video where we talk specifically about the organic chemistry to make hemiacetal cyclic glucose.